think the light changed. It is a little bit too lighter here. Maybe they put light. All right. It was quick cafe break, but we have to continue. We're going to have another very interesting session on human-robot interaction, and the first speaker is going to discuss the apparent mass of collaborative robots, and this is Sebastian. Where is Sebastian?
Yeah, online.
All right, online. So we're going to have you projected now in the room as if you are here, and then you can start sharing. So can we have Sebastian, please?
So you can hear me loud and clear?
Yeah, we hear you.
Perfect.
But
Okay, I can already share my screen.
All right. Yes. So, Sebastian, you have about 12 minutes, 12 minutes of presentation, and you will have a few questions, in total 15 minutes. All right?
Perfect. All right. So thank you for the nice introduction. My name is Sebastian Herbster. I work for the Fraunhofer IFF in Magdeburg, Germany. And I'm really happy to present today some of our research about a new approach to estimate the apparent mass of collaborative robot manipulators. So let's explain first what's the motivation of our work. So we want to guarantee safety in physical human-robot interaction. And in the closest form of cooperation, you have the collaboration. And in this collaboration, it means that human and robot share the same workspace.
Sebastian, somehow you didn't share your presentation. Can you go down to the share?
Okay.
Okay, thanks.
Now you are. Yeah.
You are here.
Perfect. Okay, sorry. So, but let's start with the motivation anyway. So we're
Please, Sebastian, put it in projection mode. Yes, perfect.
It's okay now, or?
Perfect.
Okay. So we're talking about the closest form of cooperation, which is collaboration. And in this form of cooperation, physical interaction is desired or even necessary. And of course, also unplanned collisions could occur. And that's why robots working in this mode must be equipped or must be run in the power and force limitation mode. And in this mode, there are predefined limit values for force and pressure for each body part of the human. As a result, today you have to do experimental validation with a biofidelic measurement device at the end of your installation of the robotic system, and this device emulates the stiffness behavior of the human soft tissue. But what does this mean? So if you want to set up a robotic collaborative work cell, you will start with your virtual design tool. There you will define a default velocity, calculate your cycle time and everything based on that. And next, you will go into installation. And in the installation, you do tests. And those collision measurement tests often reveal that the velocities you had in your virtual design tool don't meet those biofidelic limit values. So you have to go back in iterations, and this is very time consuming. It's consuming and cost effective before you can do into usual operation. So the big challenge is that those loops, you usually don't want. So that's why we say, okay, best way would be if you could already calculate somehow a safe velocity inside your virtual design tool. Because like this, you can go directly into installation of the robotic work cell with your safe velocity, and finally go to usual operation and skipping this time-consuming experimental validation. And the question we had to this topic was then, is the apparent mass suited to predict the safe velocity, and how must this apparent mass be calculated? To understand what kind of collisions exist, we have to look at a little bit of background. So there are different kinds of collisions, so we have to differ between the time constraint, so it could be transient, which means a short collision, or quasi-static, which means a long term, and we have to differ between clamping and free collision. And the work I'm going to present today focuses on the free transient collisions. In literature, we find different models to modify or to calculate the impact force. So basically, the most simple model says that mass of the robot collides with the mass of the human. In between is a spring, and we can reduce the system to the system on the right, where we only have one impact mass fixed to a rigid body via a spring, and we can calculate the impact force, or also the velocity if the impact force, maximum impact force, is given. So the question is, so you have a multi-body system of robot. How can you somehow project this to one directional point mass with the same velocity of the impact point? Understand a little bit more, we have to look how collaborative robots are usually built up, because they have elastic components in their drivetrain, which are mainly the torque sensor and the harmonic drive gear unit. And as an effect, this elasticity decouples the drive and link inertia. So it means that our single robot mass is at the end not one mass, but there are two masses. This was already proposed by other publications. So we have a drive mass and a link mass, and in between there's the stiffness of the links. So next we have to parameterize this kind of model. Khatib presented a mode to project this point mass matrix M of a robot to a directional point mass. And the interesting thing here is that you can calculate this mass with or without the inertia of the drive. The same thing you can do for the transmission stiffness. So each joint has its own stiffness, and you can project this transmission stiffness also to the impact point, which finally leads to a model that we have the mass of the drive, which is the result from the calculation with joint drive inertia, and the mass of the link, which is the result without the drive inertia. We can now look at this model that, so this robot with elastic joints collides with a human body, with a soft tissue. We can formulate differential equations for each mass. And as a result, we can also solve those differential equations if we have specific assumptions. For example, those assumptions are that you have linear springs, everything is at the initial position, and that drive and link move at an equal velocity at the beginning of the simulation. Also, for those free transient collision, we can we do not have to look at the effects of the controller, because those impacts are usually very short, and the controller has no chance to put any energy into this kinds of collision. So if we solve this for the deformation between human and robot, which is the interesting part, because here the impact force occurs, we get epsilon1 over time. And as we can see, this function is a function of an oscillating function by two sinusoidal shapes multiplied with the velocity. Based on this oscillating function, we can also calculate the maximum impact force, because this correlates with the maximum of the impact of this oscillating function. Finally, we can say, okay, we've calculated an impact force now for this oscillating function. And if we go back to this very simple model where two masses collide, we can now ask the question, okay, which mass did the robot have, or which mass of the robot was effective during collision, so that we got this impact force. We have evaluated this for different situations. So on the graph on the right, you can see the apparent mass over the effective stiffness of the robot, which means that we have changed in each simulation the stiffness of the robot joints, and the lower line symbolizes the mass of the link inertia only. The upper line symbolizes the sum of mass of link and drive. And in between, you can see the colored lines. And those colored lines represent different biofidelic configurations of the human. As you can see on the table on the lower right, there are different configurations depending on the body part. For example, you have the abdomen, which is very soft and very heavy. And on the other side, you have the hands, which are very light but quite stiff. And as we can see, you get an S shape from the lower mass to the upper mass bound. And depending on the mass and stiffness of this human body part, this S shape is shifted to the left or the right. And also in this graph, I've indicated this gray zone. And in this gray zone is the expected stiffness of usual collaborative robots. So what does it mean? So it means that the apparent mass of the robot is not something which is only dependent on the robot itself, but it's also dependent on the colliding human body part. So it means if you have a very heavy and soft body part, you have to take the drive inertia into account. And if you have a very light and stiff body part, such as the hands, you can neglect this, the drive inertia. And we asked the question if we can also see this effect in experiments. So we build up the following experimental setup. We have, in this case, an EVA 14. This EVA 14 is equipped with a force sensor and an impact tool. The impact tool has a wave spring to simulate the contact stiffness of the human soft tissue. And this collides with a pendulum of different mass at different velocities. Now you can see a quick video how those experiments look like. So in this case, we have the configuration 1 of the robot. It's a point-to-point movement colliding, and the robot collides with a pendulum of 15 kilogram. Now the same video again with slow motion. In configuration 2, again, point-to-point movement in another joint configuration. We can see the robot colliding with a lighter body part of 4 kilogram or lighter pendulum. And in configuration 3, we have a linear movement with a very stiff spring of 120 Newton colliding with the 15 kilogram pendulum. Next, we evaluated the experiments for the different robots we have used. So we have used an EVA 14 and a UR10. We have evaluated in each box, you can see here, the apparent mass over the different configurations. So the configurations include different springs between 10 and 120 Newton per millimeters, and the two pendulum masses of 4 and 15 kilogram. The two horizontal lines in those graphs represent, again, the mass of the links only, and the total mass of links and drives is the upper line. In red, we can see the simulation result, and in blue, the experimental results. First thing we have discovered in our experiments was that the impact velocity was, the apparent mass was independent of the impact velocity, which is great because this helps us to estimate the impact velocity based on the apparent mass. Second, we saw, as already seen by the simulations, that the lower the contact stiffness, the higher the apparent mass of the robot. We also saw that a higher pendulum mass increases the apparent mass of the robot. And finally, we can also see that the middle predictions, so the red and the blue bar, correlate quite well. What's the conclusion of our work? The first research question was if the apparent mass is independent of the impact velocity and is therefore suited to estimate the safe velocity. And it's a clear yes. But a second question makes it a little bit more complicated because we have discovered that the apparent mass cannot be generalized, but it must be given dependent on the human body part. And this makes it more complicated than we thought at the beginning. So what's the proposed solution? We think that it could also be a solution to use this analytic solution we have provided. So you can directly calculate the maximum of this oscillating function. And if you then know the maximum impact force or maximum impact energy, you can directly calculate the safe velocity. So what's the outlook of our research? We, of course, want to look at nonlinear effects because you could imagine that especially the human soft tissue is not linear. We want to see how it's easier to parameterize this model because often things like joint stiffness and drive inertia are not given by the manufacturers. And last but not least, of course, we also want to close this gap that we find a model for clamping situations. Thank you very much. Yeah, and I'm now happy to answer your questions.
Thank you. Questions? And also those who are online can ask questions. I see questions coming from, yeah, please. Microphone.
Thanks for your presentation. My question is, how you deal in your model that...
Please tell your name.
I'm Philippe Bidot. Sorry. The question is, do we need to deal with the fact that the human is not a passive system, but an active system? And so you consider the mass, but maybe it's not the only thing you should consider. Am I right?
Yeah, we thought about this too. So basically the human is also a multi-body actuator with elastic joints, you could say. But the thing with the human is that those joints are much more elastic than those of the robot. And this leads to that those masses are in most cases decoupled. So if you collide, for example, with the hand, the joint of your hand is that soft that only the mass of the hand is effective during collision.
Okay, other questions from here or from those who are online? Well, while waiting for another question, let me comment on one aspect of the model you have. I'm very glad to see the work on safety continues. This is wonderful. Now, one of the advantages of an EVA KUKA torque-controlled robot is that it almost eliminates the inertia of the rotor. And that means we do not really have to worry too much if we have high bandwidth torque control. The apparent mass does not really account for the drive mass because it is eliminated by the closed loop control of torque. And this is something you probably you would like to look at more closely. Once you get full torque control, you remove, basically you get a pure torque source, and the mass of the drives disappear, the rotor inertia disappears. Otherwise, the rotor inertia still is in the mass matrix in joint space at the joints. I mean, you can add it there, but you don't have that flexibility and those modes if you have the high bandwidth. So this is one important thing. I don't know if you probably can test it with your setup.
Yeah, so this was basically, we thought that this is the case, that you can neglect the motor inertia always. But that was exactly the point which we have seen in our experiments, that depending on the colliding body part, the apparent mass of the robot increases. And this can only come from the motor inertia, because the input from the drive, so the energy of the controller, is even far beyond decoupled from this collision, because you have this elasticity in between.
Yeah.
And this was I think this was the main new thing we have found out here. Ooh. That even for this EVA with torque control, you cannot always neglect the motor inertia.
Yeah, I mean, the motor inertia comes to be added to the diagonal element of the mass matrix in joint space, but you don't need to worry too much about the compliance that you have between the rotor and, in the drive, because of the fact of torque control. Anyway, I don't want to go too much into this. The other part is when we have collision between a human and a robot, we do not predict where it's going to happen, in the abdomen or in the head or wherever it is going to be, and which means that we really have to deal with the most dangerous part. And that's why we have the HIC, the head injury criteria, that brings like the most critical incident that can happen, because robots can collide at many different locations. And so the analysis is very interesting to see that the compliance in the body accommodate higher velocities and higher masses, but what the most critical part is the head, and this is where we have to reduce everything so that accidentally we do not make a collision with the head. Sebastian, what do you think?
So if you do the risk analysis, I think because the problem is with the head, that the head is very stiff, so you have always very high contact forces. So if you have a collaborative scenario in your industrial environment, you should always have to look that your robot moves at a height where it could never hit your head, because then your robot would have to move at very low speeds. Instead, today there are so the head injury criterion, I think it was at the very beginning of the collaborative robot used. But at the moment, so there are predefined limit values of force and pressure. And those values are defined for different body parts. And if you put a collaborative work cell into operation, you have to do a risk analysis. And then, for example, say, okay, if you have a movement during a pick and place task, the robot moves down, it's very unlikely that your head gets hit, but instead you have to do the risk analysis for your hand, for the back of your hand.
The intersecting workspace. So Sebastian is going to continue with the next paper, and he's going to talk about the hazardous potential of collaborative robots. Sebastian, why don't you share the next presentation?
Does it work now directly?
Yeah, it is perfect. Thank you.
Okay, so thank you very much. So in this second paper, I'm going to talk about a new conversion method to evaluate the hazard potential of collaborative robots in free collisions. The research of this project was founded by the Rossini project, we're a partner of. The Rossini project is a European project called Robot Enhanced Sensing, Intelligence and Actuation to Improve Job Quality in Manufacturing. So again, we are basically talking about the same motivation like in the first topic. So I will keep this a little bit shorter. So we have again collaboration. We have to do power and force limitation, and we are focusing on in this topic now on the experimental validation with this biofidelic measurement device. Because the problem today is if you have found out in your risk assessment that your robot could have a free transient collision with the human, you use this biofidelic measurement device shown on the left. And this biofidelic measurement device is always fixed to a rigid structure. And if you now measure the contact force with such a fixed measurement device, you will have much higher contact forces as you would usually have in a usual collision. So it means at the end, your robot moves at a much lower speed than it could. And this is, of course, a high loss of productivity. And we ask a question if it's somehow possible to convert these measurement values of the fixed measurement device with a conversion method into a free collision. So in this case, we developed a mechanical model. So on the left side, you have the same model of the robot like in the previous topic. So a robot with elastic joints and moving masses. And on the right side, you have the biofidelic measurement device. This biofidelic measurement device consists of a damper material, a bumper, a spring, and underneath the spring is a force sensor, which measures the force over time. In case you have a fixed measurement device, this force sensor is fixed to a rigid frame. In case you have a free measurement device, it's attached to linear guide rails. You can simulate this as a one-dimensional system as shown on the bottom. So you have again the robot with the drive inertia, transmission stiffness, link inertia. Then on the other hand, the measurement device with all the springs and masses. If we further simplify the system, again, we can say, okay, the fixed device is just a robot colliding with a spring. And in case of the free device, you have the robot colliding with the total mass of the measurement device. And in this simplified or abstracted system, you can calculate the impact force analytically, directly. And if you build a quotient between the two, you can see that it's possible to calculate the free impact force based on the masses of human and robot. But of course, this means that you have to know both of them. So the mass of the robot in this clamping situation, you can calculate from the momentum of the impact force. As you can see on the lower graph, you have the force over time signal, and you can build the exact integral for the momentum, or you can even do a triangle approximation. And from this, you get for even specific velocity, even every specific joint configuration, the mass of the robot. On the other hand, you have the colliding mass of the human. Within those experiments here, the colliding mass of the human is just the mass of the measurement device itself. And in case of a real scenario, you would get those values from the ISO TS 15066. If we simulate the system, get the following results. So in the graph, we can see force over impact velocity, so maximum impact force over velocity. And for the fixed measurement device, you get the highest force values shown in yellow. The next, you have the simulation results for the free measurement devices with the solid lines in blue and red. And if you now have a certain limit value for your body part, for example, this horizontal line at 280 newtons, it means that for your fixed measurement device, you would only be able to go at 280 millimeters per second. But if you have a free measurement device, so free moving body part of the human, you could almost go twice the velocity. For the next step, we applied the conversion method to the fixed measurement results, and the result are the dashed lines. And as we can see, those dashed lines correlate quite well with the simulation results for the free device. So in total, we have seen that it's from the simulation side, it should be possible to have this conversion method working. And in the next step, we want to see if that's also can be seen in practical experiments. For that reason, we have attached this biofidelic measurement device to a linear guide rail, and we added the possibility to add additional weight to simulate different body parts of the human, different heavy body parts of the human. On the next slide, we can see some videos. So this first video, the UR10E collides with the fixed measurement device. We can see the robot bounces back due to its elasticity. In the second, the robot collides with the 7 kilogram measurement device. We can see that the measurement device is accelerated by the robot. And in this last video, we can see the robot colliding with a measurement device of 23 kilograms, so quite a heavy body part. And we can see that it's less accelerated. We have repeated those experiments with in total 3 different kinds of robot with various payloads. And for every payload and configuration, we have created the following graph. So here you have the impact force over velocity. And just as already predicted by the simulations, we can see that the fixed measurement device in green has the highest impact force, followed by the 23 kilogram measurement device and 7 kilogram measurement device. You can also see that for the lightest measurement device, the admissible velocity can almost be doubled. So you can go at about 640 millimeters per second without injuring or harming the human. Next, we have applied the conversion method. So it means you only have the results of the fixed measurement values available. From that, we get the maximum impact force, we get the mass, the effective mass of the robot, we get the mass of the human, which is in this case the mass of the free moving measurement device. And from that, we calculate the maximum impact force of a free impact. So the result are those lines in green and blue. And as we can see, we get almost the same speed increase like we have seen in the experiments with the real free moving measurement device. And this looks already quite good. And for that reason, we have in next step looked at all measurements we have done, looked how accurate is this conversion method. So in total, we had about 1,000 measurements in total, or 1,000 collisions of a free moving measurement device. And also the same amount of measurements for the fixed device, and converted all those results with the conversion method and compared it to the maximum impact force of the real experimental results. The result are the 2 graphs on the right. So this histogram, where we can see the relative error and the absolute error, and everything to the right side of this red vertical line means that the calculated or converted impact force is conservative. It means we have converted it to a higher force, and a higher force means in the next step that we have to go at a lower velocity, and the lower velocity is always safe compared to a higher velocity, or safer compared to a higher velocity. But I forgot to mention, so we have those 2 different colors, and those 2 different colors in red and green come from different approaches to estimate the mass of the robot. So in green, we have the exact integral, which leads to higher masses of the robot. And in red, we have the triangle, which leads to a little bit lower masses of the robot. As we can see, for example, for the triangle approximation, 95% of the converted measurements values were conservative, which means that we are in 95% of the cases we are safe compared to the experimental validation. So what's the conclusion of our work? With this new method, we now have the opportunity to convert measurement values of a fixed measurement device into such that would occur with a free measurement device. The thing is, I did not mention before, so of course you could also in your real experimental validation always use a free measurement device, but the problem with the free measurement device is that it's very bulky and that you can only use it in movements of the robots with a horizontal plane. So that's also a reason why we want such a conversion method. Due to this conversion method, we can now have significantly increased speed and productivity of the robot. And this, as you have seen, especially for very light body parts, this means that we can sometimes double the velocity of the robot and while still being safe. As an outlook, we're currently working on that you can also estimate the speed of the robot, the impact speed of the robot based on the force signal of the impact, because in many cases you have the problem that this velocity is not known, which is especially true for point-to-point movements, and if you're an integrator and not the robot programmer himself. So thank you very much for the opportunity to present the second topic, and I'm now happy to answer your questions.
So, Sebastian, please stay on. We will need you at the end of the session for the discussion. And because we are really late, we will keep the questions to the end at that part. So, Thomas is here. Thomas is going to talk about curiosity. So I'm going to switch to curiosity. All right.
Thanks. So my name's Tom. I'm from the University of Southern California. I work in Maya Matarek's Interaction Lab. I'm going to be presenting on work I actually did with a bunch of my undergraduate students. Those are all the other co-authors on kinesthetic curiosity towards personalized embodied learning with a robot tutor teaching programming and mixed reality. So kind of just to give an idea of what our lab does, we work in socially assistive robotics. So this is a subfield in human-robot interaction where we focus on social dynamics, so modeling and how do we really work in more of the social side. And we usually work with more vulnerable populations, so older adults or younger students. So we have an example here with our robot Kiwi, and actually a student who has autism spectrum disorder. And Kiwi is teaching the student math. This was a long-term deployment. So our robot tutor situations typically look like this. We have a robot and then a student sitting at a tablet working with the robot to do something. So how I like to frame a lot of these robot tutor things is we have some sort of state space. We have the robot, the user, and the interaction. The interaction would be the tablet, the games, that sort of thing. And then just some examples, the robot's doing some sort of action. The interaction has some current exercise. And then one interesting thing to note is we do some user state affective or cognitive estimation. So something like user engagement or their concept understanding. Then we have the action space, both the robot and the interaction. The robot can do certain things. And then the interaction, move, exercise, stuff like that. In the robot tutor world, you'll see a lot. They'll actually just model this as one big action space and say the robot is moving the interaction forward. And then the end goal is to find some mapping. Today, I'll be focusing on this user affective or cognitive state. How can we expand that state space? So the classic example in the education world is doing how do we model student engagement. Engagement, and I'll be using the word curiosity later, is just a high-level psychology term. They're all super, super context-specific and mean something completely different across all the papers. So I'll try and keep mine very specific when I talk about curiosity later. But engagement in this context would be you model some logistic curve. You just see how long a student is taking to respond to questions. And if a student's taking a long time, probably disengaged. If this happens over a long period of time, the robot should probably engage in some re-engagement strategy. So we wanted to get students out of their seats. And we wanted to move from kind of a 2D space to a 3D space. So we looked at augmented reality. So here's a GIF of the HoloLens 2. Augmented reality is where you can see objects, virtual objects projected in a 3D space. And those objects can interact with the world. You can have a virtual ball that bounces and rolls around. But you can still see the world around you. So that was really important to us. And in order to explore this, we created a 3D Scratch or 3D block-based programming language that eventually will be with 4th and 5th grade students. Students did exercises alongside a robot tutor. So kind of the key insight from this work is we first propose and evaluate a personalized multimodal measure of student kinesthetic curiosity, which combines student movement and curiosity scores. And then something I think is a little bit more important actually is we did a within subjects pilot that supports further exploring unique multimodal user data afforded by augmented reality interfaces. Basically in our normal interactions, we have external cameras that are pointed at a student, and then a student moves like 5 feet over, and all of your stuff doesn't work anymore. What's great about AR interfaces, such as headsets or even phones, you have this idea that the person is wearing it or it's in their hand. So it's a lot more consistent. So like I said, we developed Move to Code. Here is a Hello World example, kind of the canonical computer science example. And then some other things that we have also implemented. Students can drag blocks around and do math. More recently, we've put for loops, arrays. You can visualize memory, variables, stuff like that, and even control the robot. So to kind of score student movement, we look towards the field of embodied learning, kind of colloquially known as kinesthetic learning. So we wanted to see how students would move to learn. Actually, ironically, the Cypress Interaction Lab does really good work on embodied learning. This would be one example, students jumping on different answers for math problems. In the embodied learning world, there's kind of two axes. There's how much does the student move, and then how integrated is the learning. So this would be an example of high movement and kind of low integration, whereas they have another experiment where they have people's arms, they connect arms and make angles, and that's very integrated into the learning itself. Kind of an interesting sort of psychological view on it. So for curiosity, this is measured all over the place in different ways in human-robot interaction. One example is out of Curiosity Lab. They had a robot do poses and then had the person do different poses, and then they can quantify how much variance they have in their posing. And then a more classical approach, which is what we end up taking, is out of Waterloo, where they have some sort of topic, and in this case, rocks. And how many questions is a student asking about rocks? Are they still wondering about it later? And how many things are they interacting with? So in Move to Code, what we did is we created a movement score and curiosity score, which are sliding windows. So the application runs at 50 hertz, so grabbing a score of 0.02 seconds doesn't give you very much. We take the head pose over time, over about 20 seconds, and that will be your movement score. And then we take your curiosity score is how many information-seeking actions have you done in the last 20 seconds? And an information-seeking action is super context-specific. And back then, this is 2 years ago, this was defined as basically any time someone grabs something or moves something around. So we had these two scores, great. They have different units. We wanted to combine them and personalize them to each student. So we actually thought about z-normalization. So you just take the student's average and variance. You can just iterate that over time for both these scores, and then you can normalize it out. And then we can add those together and assign weights based upon which one we care about, and that'll give you a real-time score for students' kinesthetic curiosity. Another great thing about this is if we want to compare the human to the robot, their action spaces for this score is the exact same thing. How much is the person moving, how much is the robot moving, and how many things are each of those individual things moving or doing. This is a problem in HRI where we say we have a more curious robot or a less curious robot. What's great is now we can actually compare how curious our different robots are in different interactions. So we did a pilot study. We ended up with 9 participants. We had 10, and then one had to drop out for 20 minutes within subjects. We had a more curious robot and a less curious robot. I had these thresholds. I'll show the very large mapping here of what those thresholds actually mean, but really all you need to focus on is this virtual information-seeking action versus positive physical affect. Based upon the thresholds, we would do a virtual information-seeking action, otherwise known as just a curious action by the robot, such as doing something in the interaction or trying to ask the student to do something. And then if it's below the threshold, we just did some generic positive physical affect. And then we had a time since last action, so the robot's not just spamming actions over time. So the first hypothesis was really about QC depends on stationary mean and stationary variance. So we tested that for all the participants and found that that holds true for all the participants. The second was the robot did all these virtual information seeking actions, and 170 in total across all 9 participants. We want to see, did that have an effect when the robot actually did it? So when the robot would do one of these actions, we would take that score, and then the score 20 seconds from then, compare them, get those deltas, and that's what you can almost see up here. That is a terrible color on on a projector, though. We did find that there was an effect. I would argue it's not super strong. So technically, we do see a short-term effect when the robot would do these things. But you can ask me another time as to what I think that effect actually is from. So this is the last one, was essentially between the two conditions, the more curious robot and the less curious. So on the left side, you see all the raw scores of movement and curiosity for the students, and then the curiosity score for the robot, and then those are normalized on the right side. So we looked at the student movement and curiosity scores and found no difference, which is pretty evident from the graphs themselves. But we did find a difference in the robot curiosity, which is great because we chose these thresholds, and the robot was more curious in one scenario versus the other condition. So limitations, I was joking with some people in the back. I could write like a whole paper on the limitations of this study that we did 2 years ago. We've done a lot since then. And actually, we're super excited. I'm still working on this. I was working in my hotel room last night on this too. We're running a study in 2 or 3 weeks with kids. We can do this virtually now. We have a high fidelity virtual robot. And now, as opposed to the headsets, we can actually use phones, which work really well. And we'll have students actually being able to interact with our stuff. Hopefully, that's at least the plan. So I just want to thank my huge research team. Most of these people are all undergraduates. And then Karen and EPEC are the ones on the new project. And obviously, I'd like to thank my advisor and NSF for funding me. I just want to leave it on the key insight from this, both on the student kinesthetic curiosity and the idea that we can explore more of these unique data that are coming in and combining them. And then I've gotten a lot of recent interest in virtual, augmented, and mixed reality for human-robot interaction. We are putting on our 5th annual workshop this year. It just got accepted. So if anyone's interested in that or has any lab mates who are super interested in that sort of subfield, please, by all means, reach out to me. Thanks.
Questions? Yeah, please. A microphone over there.
Tom, you mentioned that you can sort of choose the weighting between the two factors. How would you, in a study, because you're proposing this new thing, how would an end user sort of choose these weights?
Yeah, that's one of the largest, probably the largest limitations. To me, it depends on what the teacher wants, right? So do you really care about a student's movement or curiosity more? And I think dynamic weighting throughout the exercises is more interesting. So you can curate the content. So content is king, and you make a ton of content. And then you base those weights based upon what the content for that particular exercise is. But yeah, for this study, it was basically arbitrary, just put them even with each other.
Harsiman, could you please turn on your camera? We're going to prepare you for the next lecture. Other questions?
Yeah, sure.
Okay.
The question was, how do you decide what a good experiment is? You argue about what's terrible about your experiment for like days and weeks and weeks and weeks. It's really hard. To me, because I've been talking a lot with students and especially undergraduates, you pilot your experiment a ton. And I think that's something we don't do enough as a field, is just mini pilots with a bunch of people and then realize all the faults that are wrong with it. Because you can plan it all you want and do all the experimental analysis beforehand, I think. But you're going to run into something that's just a huge confound, and you wouldn't have been able to predict it without giving it to people.
Well, thank you very much. Thank you again. All right, so Hasibran is here, and the next talk is going to be about transparency in haptics. And we have 12 minutes of presentation and 3 minutes of discussion. Please, go ahead. Thank you.
Okay. Thank you very much. I hope you can hear me loud and clear. Okay. Sorry, can you hear me? Just a confirmation.
Yes, we hear you.
Oh, okay, great. Thank you very much.
Thank you.
So I would be presenting work on a new haptic rendering algorithm, and that would be amalgamated with time domain passivity approach. My name is Harsimran Singh, and I'm from DLR, Germany. So what are haptic displays? We see that haptic displays can either be kinesthetic haptic devices or tactile haptic devices. And kinesthetic haptic devices are devices that could be used to display force or motion information. And that is the one that we are interested in this research here. There are a lot of things that could be done using the kinesthetic haptic devices. For example, doing some telenavigation, as we can see on the left. Let me turn on the laser pointer, or doing some telemanipulation tasks. Here we had an astronaut on the ISS control robotic arm on Earth and then pick up some rock samples. Or we can have some medical usage where we have some robotic minimally assisted surgeries with some force feedback. We all know there is a trade-off between stability and transparency, where if we have an impedance type device, which can provide very nice and crisp force feedback, it's a multi-dock device, usually 3 or 6 degrees of freedom force feedback, and it can give a very good rendition of free space. However, impedance type haptic devices have low inertia, and they have usually less friction so that the human can move it around in the environment freely and easily. And that is the reason that devices sometimes become unstable when we are trying to render some virtual environment. One easy solution to this is adding a virtual damping, which can make the haptic interaction stable. But then the downside to that is that it decreases the impedance range, and it also decreases the hardness perception that the human operator feels. So in a way, if we have a device that we need to differentiate between different virtual environments and their stiffnesses, and then we add some form of controller, and that takes away that possibilities, then it's not that fun to use the device anymore. So the problem is the inherent trade-off between stability and transparency. And one of the solutions that we proposed before was to use an approach called successive force augmentation approach that we proposed. So we showed that if we use SFA with any impedance type haptic devices, we can make the interaction stable. We can increase its impedance range. So for example, the device can then render stiffnesses starting from 0 all the way to 10, whereas before it could only display stiffnesses from 0 to 1, for example. And it can also enhance something called a rate hardness, which is the human's perception of how hard or soft object is. And just a little background on why the haptic interfaces go unstable. So we see on the left, we have a human operator interacting with some form of haptic device, and then it goes into the digital side aspect of the controller, where we have a controller and a virtual environment. So this is all in the digital format. And then we see that the energy going into this haptic interface is much less than the energy coming out. This is due to the effects of discretization. And that's why the system becomes unstable and it becomes active. It might not become unstable, but it becomes active, which might lead to instability. So if we look at the virtual environment, let's say it's rendered as a simple spring setup, as we see here. And on the left, we have a force versus position of this haptic interaction point, the dot in black. And on the graph on the right, we have an energy versus position. So we see as the haptic interaction point moves inside the virtual environment, which is, let's say, a human operator trying to interact with the virtual environment, it's called the pressing path. And we see that as the penetration depth between the virtual environment increases, so does the force. And so does this energy, which is the energy into the system. However, now when we move the point back out of the system, which is called the releasing path, we see that the energy goes into the negative domain. So it's no longer passive. The system then becomes active. And this is the energy that we need to eliminate from the system to make the system passive and therefore stable. That is the unwanted energy generated in a system because of the effects of discretization. And this is a real experiment using a phantom premium, we see if we have force versus position on the top for a very small stiffness, the interaction is stable. It somehow does not diverge and it converges at some point. The stiffness here was 0.5, and using phantom premium 1.5, the same device, we see at the bottom that the interaction goes completely unstable and diverges when the stiffness is higher than what it could stabilize. In the past, there were many stability-based approaches that were proposed. They were passivity-based, and then a little less conservative absolute stability-based, and then there were even less conservative input to state stability approaches. And the approach that, so a little going back to what's actually successive force augmentation approaches, and then we would come to what we have proposed for this paper. So what SFA proposed says that, let's say we have a really high stiffness of the virtual environment that we want to attain. We start with a very small stiffness based on Colgate's passivity theorem, which says that it should be less than 2. B is the physical damping of the actual device that we are interacting with, divided by the sampling time. So we have this very nice small stiffness. So if we always follow this, the system would be stable and we would not have any instability issues coming up. And then the releasing path again follows the same stiffness value. And if you stick with this value, then you always diverge or always converge somewhere at this point. You would never be able to reach up to the desired stiffness value. So then what we do is we introduce offset, feed forward here. And what it does is that in the next interaction cycle, rather than following this line here, we follow the line on the top of it. And if we look at the energy consumption or the energy generated during the first interaction cycle, we see that it's the input energy, which is the green shaded area, plus the output energy, which is the shaded area on the top. And this would always be less than the energy dissipated by the physical damping of the device, because of we choose it based on Colgate's passivity theorem. So we parameterize it accordingly, and then the system is stable. And as we continue this iterations, by adding this offset based on some value alpha, we see that the graph on the right keeps moving further and further up. And then we started from a very low point there, and then we reach to a higher point here. So if we keep on this cycles, if we keep interacting with the environment and not move out of the environment, we would also reach at the desired point that we have to reach, which we would show in the some plots here. So we see the stiffness is pretty high on the right, not so high on the left. So on the left, we don't have any controller, and we see that the system diverges and goes unstable. Whereas if we have the same system on the right with the same experimental setup, phantom premium 1.5, but even a very high stiffness, we see that it starts from a very low value, but it reaches up and reaches the actual desired stiffness, which was 10. That is what we wanted to attain. This is just an experimental setup showing if you interact with the virtual environment, your system is very jittery. And then if you use the SFA approach, then the system becomes stable. You don't hear any sound, and it's very smooth, and it can render higher stiffnesses as well. However, one of the drawbacks, okay, this is just the same data that we saw, but also with position and force information as well. One of the drawbacks of this is the rate hardness. Even though the displayed stiffness is higher, it gets higher with time. But when you make contact with the environment, the user cannot discriminate if the environment is crisp or it's something very soft at the moment of contact. So there was the extended version of SFA to enhance rate hardness, which is as shown on the right. So on the left is the previous version that was explained now, and on the right was the extended version of the SFA. And what it does is explained here. So rate hardness, it's the rate of change of force by rate of change of velocity during the initial contact of the haptic interaction. And then what we do is during the initial contact, you follow the real high stiffness of the virtual environment. So no matter if the stiffness is 5 Newton per millimeter or 10, you follow that straight away. And on the releasing path, then you follow the smaller stiffness and not the higher stiffness anymore. One of the drawbacks of this is that when you're following the small stiffness on the way back, once you exit the virtual environment, which is shown here by the dotted line on the graph above, you might just fall down and the force might become 0. And this force would increase, or the force discontinuity would feel even more absurd if the stiffness of the environment is higher. So if we look at the previous graph, the stiffness was smaller and the force drop was not that high, but here we see we would even have a higher force drop, which is not what we want. So to fight this problem, we extended the virtual environment's boundary conditions. So let's say the virtual environment starts. So when you make contact, the virtual boundary starts from here. But when you exit contact, rather than stopping here, it sort of moves back a little bit. So we have some delta X here, which is not that bad. We conducted some user studies. So I would show it to you in the next slides. And no user could tell the difference between the shift of this virtual wall here that we had. These were some of the data, and the point to notice here is this plots shown in the black boundaries. So here we see what we describe as rate hardness, or what was described as rate hardness earlier, and we just adopted the terminology. So we see when you make contact with the environment, the rate hardness is actually the actual stiffness that the virtual environment should render. It's 3 in this case and 5 in this case. So when we used this approach and we conducted some user studies where we had 2 haptic devices on the left and the right, both phantom premiums. And then on the left, we had no controller, and on the right, we had an SFA with with the SFA controller with different virtual environments. And then we saw that when the user, and which were randomly arranged, and when the user interacted with these virtual environments, they could accurately discriminate between them. So the significant difference could be clearly seen from these experiments. However, another drawbacks of even though the extended SFA version was this energy generated. So it was not stable for all the haptic interactions. For example, if you had a device which was really lightweight, then you could not render very high stiffnesses with it always, because then we would have some really high energy generations, which would lead to instability. And to counter that, we propose that instead of using the same small stiffness from the point where the releasing path starts, we make contact with the very high stiffness, but the pressing path, the first pressing path of the interaction cycle then follows this smaller stiffness. And as a result, we see the generated energy in this case during the first cycle is much less compared to the one on the left. And then we had this algorithm that we followed, which basically says that for the first interaction cycle, follow the high stiffness, and for the next pressing path, or for the next releasing and pressing path of the consecutive pressing cycles, we use the same small stiffness, which is KV, which was proposed by Colgate. And however, we still had to be sure, or wanted to be sure, that the system would still be passive. And if we see that this right now, the SFA plus virtual environment, although we cannot conclusively say it was active, so we had to introduce a passivity observer, a passivity controller, and then the output force then would be modified such that the overall system is passive and therefore stable. And the experimental setup used to test out this controller was Panda, and then we used Phantom Premium. So Phantom Premium was used as a haptic device, and this was the remote robot that interacted with the environment. For the first set of experiments, we saw that we used the Phantom Premium and the Panda just to interact with a virtual environment. So for the Phantom, it was 8 Newton per millimeter, and for the Panda, it was 30 Newton per millimeter, which would have been unstable if we did not have this controller. And just to show you what the experiments were like, so we wanted the user to feel the same feeling as if he's making contact with a very hard environment. And now if you move the environment, then by using the device, you should still be able to feel something very rigid and not something that is soft. So these were the experimental results that we had. If we use the phantom premium in the first case. So we see we had a stiffness of 8 and it could stably render that without going unstable. And the next one is for Panda, which we saw in the video in the last slide, where we could render stiffnesses of as high as 30 Newton per millimeter, still being stable. So the user actually felt as if he's interacting with something really hard and not something that was very soft. And the last set of experiments that we did was in the teleoperation scenario, where we had a virtual fixture as seen by the yellow translucent box here on the right, and how these experiments were carried out. One thing I want to point out that there was no delay between them. So it was a delayless experiments. Just a schematic, this is what we do. We use a haptic device and there is a virtual environment. And there is also a real object on the remote side. So the user has to discriminate if he's interacting with the virtual environment or if he's getting the force feedback from the real object. And we were using a force measured force position teleoperation architecture. This was the block diagram of the schematic where we had the SFA and TDPA that was proposed with some virtual fixtures. And then we had some teleoperation architecture using position measured force feedback. So just to give an idea what the experiments were like. So the user, so if you see on the right now, there is some unseen virtual fixture that the user can interact with. However, there is no object in the real environment, but the user can discriminate between that and this, where he actually has a virtual fixture that he can feel. So he cannot move the device anywhere outside of that boundary, the virtual boundary that he has. And he can also make contact with the real environment. And then he was able to tell the difference, whether he was touching the real environment or he was touching the virtual fixtures. And this could be very beneficial if we use it in medical domain, where if the surgeon is performing some surgeries and there are some virtual fixtures, then he should know if he's actually touching the organs inside the body, or he's actually in a safe, or he's actually going out of the safe boundary, which he should not, which is for safety reasons. And so these were the experiments. As you can see, the blue line on the right is with the virtual fixture. You can clearly see a very high stiffness with the same device. And the one on the left is the displayed stiffness for the teleoperation task. So to conclude, we propose some modification of the SFA that generates less energy but still maintains the rate hardness properties. And it was combined with the time domain passivity approach for now to ensure passivity of the overall setup. And we use the experimental setup to render very high stiffnesses for haptic rendering. And then we also use it for teleoperation experiments where the user had to discriminate between the force feedback coming from the real environment versus the force feedback coming from a virtual environment. For future work, we could conduct some user studies, conclusive user studies, to find out if the users can actually discriminate that and design the SFA for time delay teleoperation system without using TDPA and just using SFA, and also extend it to other robotic systems like series elastic actuators that we tried a little bit on the right. So we saw we could also implement that on series elastic actuators, which makes the system behave much faster. So the bandwidth or the dynamic bandwidth of the system actually increases. So thank you very much for your attention, and I would be happy to answer any questions if there's any time. Thanks.
Thank you. Thank you. So while asking the questions, Nancy, could you please turn on your camera so that we can share your presentation? All right, questions? Yeah, this microphone.
Hey, thank you very much for the great presentation. In my opinion, one of the biggest issues that we have in robotics is simulating contact dynamics. And what you're doing is basically creating these artificial boundaries. Do you think you could use the same techniques to improve the simulation of like direct contact dynamics in complete virtual environments as well?
Yes, that could be the next step. So what we want to do is we want to take it over to some medical simulators or something where we have something what you're describing, so that using whatever devices we get, we could actually basically do some contact tasks where the dynamics, so it's not modeled based on the system, but it's independent of system modeling, but still you could achieve some stable convergent behavior rather than having, for example, in a virtual simulator where you have a peg in a hole tasks. It seems very simple, but it's not, because you have multiple points of contact. So the thing just goes unstable and it looks crazy. So yeah, the idea is also to have it in some virtual simulators where we can also very stably and safely without any models conduct such simulations.
Thank you.
Welcome.
Other questions from those who are attending online? Questions? Maybe, I mean, this is a very important problem, especially when dynamics come into the picture. That is, you're making contact, but you're moving at the same time, constrained motion. Mm-hmm. And so winding, unwinding, and how fast you can deal with those issues is very important. There is the concept of proxy that mm-hmm. we use in haptics, and how it's being used here, and where the model is connected to the proxy. I didn't see that explicitly in your presentation.
Oh, okay. So is my screen still visible? So if you can see my screen, so yeah. This is the proxy point here that I was showing. So the proxy point stays the same as if you're interacting with the environment and you move out. The modification is that we basically extend the boundary from this point, this red line here, to we shift it further back, maybe somewhere here. So the proxy, once the proxy is inside the virtual environment, so maybe at this point here, then this red boundary moves back. So we are still using the proxy method as the base of this rendering approach, and then we are building basically things around it.
I mean, in my understanding, the proxy doesn't penetrate the surface. It's the finger that penetrates the surface, the actual position.
Yes.
And the proxy remains on the constraints.
Yes, the proxy remains.
So I saw that this was moving inside. I thought this was the finger, not the proxy.
No, sorry. It's the haptic interaction point. So the proxy stays on the surface, and the haptic interaction point goes wherever you want inside the body.
All right. Okay. Now I see it.
Okay. Yeah. Sorry for the confusion.
Okay. Thank you very much. And Nancy is here. Thank you again. Thank you, everyone.
My pleasure.
And please stay on for the discussion. Nancy is going to present the next paper. And this is on what? Oh, this is toward robotic steerable system for high dose rate drug therapy. Oh, wow. We cannot see very well the red, but I think hopefully. Let me just put this. Okay. Now we can see you, and please speak to see if we can hear you. Nancy, you hear us? Can you speak? Can you hear us? Maybe you can remove the headphone. You remove your headphone. Can you remove your headphone, please?
Unplug them. Because sometimes...
Yeah, she's not hearing, so Okay, let me write to her.
But she can't hear Bruno. You can say, okay.
Yeah, can you-
Unplug. Tell her
Yeah,
to unplug.
unplug the headphones.
Oh, no. So we have Nancy, can you hear us?
Yeah.
Yes. So can you remove your headphone and speak directly without just using your speaker and microphone from the computer?
Yeah.
That means she should unplug them. She should unplug.
But you have to unplug your headphone.
Yeah. Oh, could be, yes. Disconnect them. Disconnect them.
So we have to turn it off. Okay.
Why don't we switch?
Okay, I'm going to go to do that. So Nancy, we are going to switch and we will try to connect you offline. Let's see if the next speaker.
That's an in-person.
Pragnamanam.
Yeah, no, Pragnamanam. He's. Oh, all right. Okay.
Oh, great.
So you are here. So Nancy, I'm going to explain to this, and we will connect you separately. Okay. If you have Nancy, if you have a phone number, you can send me, and we will call you. Okay. All right. Okay, we're going to switch you. You're ready? All right. Okay. Well, please go ahead.
Hello, everybody. My name is Kevin Zhang, and today I'll be presenting on behalf of Pragna Manam, who's a fellow lab mate, but she couldn't make it because of a family emergency, as well as my professors Oliver Cromer and Fatma Zainab Tamel from the Robotics Institute at Carnegie Mellon University. So first off, a little bit about what a delta robot is. A delta robot is a 3 degree of freedom parallel robot where the end effector stays parallel to the base of the robot. And this is mainly due to these parallelogram links connecting from the motors to the end effector. These are typically used in precise pick and place tasks in manufacturing as well as 3D printing lately. However, they're a bit large at the moment. So our goal was to make 3D printable robotic arms that have higher degree of freedoms than these typical 1 degree of freedom open-close grippers, but at a cheaper price as compared to these much higher degree of freedom hands like the shunt hand and the shadow hand. Here's just a demonstration of it picking up a pill, but mainly we want it to also be soft and compliant so that we can interact with humans better. So if a human was being fed a pill, it would be much safer to do so. So some related works are first the millidelta. So this one was a millimeter scale delta, but it relied on MEMS manufacturing, so micro electromechanical systems. It's very difficult to manufacture because it's very intensive, but it was actuated using piezoelectric actuators. On the other hand, there's this Delta Robot 1. This one's like an open source kind of Delta robot, but it relies on these ball and socket joints. So in this other thing, you can see that these ball and socket joints require manufacturing from you have to print it, like pour plastic into a mold to make the balls better. Ours are all 3D printable, so here you can just print it flat using either the materials PLA or TPU. To replace the ball joint on typical universal joints, we have 2 hinges. So one hinge goes down while the other one goes side to side. And the goal of this paper was to discover the parameters that best allow these motions so that the end effector stays parallel to the base. So we tested two different materials. One is thermoplastic polyurethane, TPU, which is the blue one, and then polypropylene, which is the clear, transparent white one. They have different properties. TPU is typically softer than polypropylene. Then we varied the hinge thicknesses. So we varied them from 0.375 millimeters to 1 millimeter. 0.375 millimeters was about the thinnest that it could print reliably, well, so that it would be strong enough. And for the beam thicknesses, we varied it from 2.5 millimeters, 3.5 millimeters, and 4.5 millimeters. The total length of the beam was constant at 27 millimeters. The depth was 4 millimeters, and then the hinge length was 2 millimeters. So we did some parallelogram characterization experiments. So we mounted these parallelograms onto this board, and we used OptiTrack to keep track of the rotation. And then we had a force sensor attached to this linear actuator that pushed the tail of the parallelogram to see how much force it would push back on. So in total, we executed 120 of these experiments. And so between these two graphs, the first one is using the polypropylene ones, and then the bottom one is the TPU. These graphs just show that the polypropylene deltas typically result in higher forces pushing back. So that scale is from 0 to 4 newtons, while the bottom one is from 0 to 1.5 newtons. And so when we push, we can see that the hinges that are 0.375 millimeters, which are at the bottom of the both graphs, typically result in less forces. So thicker hinges usually result in larger forces. So this is consistent with all of the data. Next, we wanted to use the OptiTrack markers to figure out the rotation. So the least amount of rotation is most ideal, so that it stays a parallelogram. What we found was that, again, the thinner hinges resulted in the least amount of rotations. The thicker hinges, they pushed back more, but that also meant like they typically would rotate more. So the z-axis is coming out of the frame. So using the OptiTrack, you can kind of see the rotation. All of these experiments were done with the 20 millimeter push. Finally, for evaluation experiments, we lowered one arm of the delta to see how much the end effector would tilt. We want it to be as parallel as possible, so we lowered one arm by 50 degrees. So as you can see, with the TPU print with the hinge thickness of 1 millimeter has a more slanted version compared to the TPU hinge of 0.375 millimeters. The beam thickness didn't really affect this as much. Here I'm just showing all of the different experiments, but what the end result was that for the most ideal parameters for both the polypropylene and the TPU deltas was a 0.375 millimeter hinge, but the difference was the TPU, because it was softer, it performed better when it was using a 4.5 millimeter beam thickness, while the polypropylene one was fine with 2.5 millimeters. And then 1 millimeter hinges resulted in the worst results. In conclusion, we found that the more compliant hinges performed better in our experiments, and that polypropylene parallelograms had the more minimal Z rotations and the larger forces. Now, this is laying the groundwork. I'm going to briefly talk about some following work that we presented in RSS this year. So I was a co-first author on this. We created this linear delta and used the ideal parameters that we found with this paper. And with these, we were able to show that it was compliant. This is me trying to squeeze a grape. It couldn't be squeezed very. Oops. Did it go backwards? Oops. Sorry. Yeah. Okay. Yeah. So it's compliant in that it won't be able to squeeze a grape, but because it has 3 degrees of freedoms per finger, it gives us a lot more options to move, to tilt an object, or like to roll items. So here it's aligning a stack of quarters. It can pick up a quarter by itself. Oh yeah, the total cost of this end effector was about $350 US, and we have all the CAD designs and the 3D prints, STL files of this. We can pick up a card. One of the harder tasks was taking a grape off a vine. You can't pick it up straight. You kind of have to twist it at the end. So we can also change the fingertips on these deltas just by screwing and putting on a new one. So most of these were teleoperated, of course, but yeah, here's the rolling dough. This is 5 times at teleop. I might try to speed it up. Okay. Here we go. Yeah, it's definitely challenging. We're working on making it more autonomous and have force sensing in the future. But yeah, thank you all for listening. And if you have questions about the work, the first author's email address is there. And this is also a grant from NSF.
Thank you. Questions?
Thank you for this presentation. It was very interesting. I would like to ask, what happens if these end effectors face with a force? Is there any plastic deformation happens, or are they really stiff? How can be repeatedly used?
So that's the funny thing. I just added this slide. This is me hitting it with a water bottle. This is actually filled with water, so it can take pretty good beatings. Oh shoot. Okay, I slam it with the water bottle, it's fine, but if it stays for extended amount of times, there is some extended deformations. But this, in general, we haven't had any problems with it breaking with these parameters so far. But the TPUs are softer, so it tends to bounce back faster than the polypropylene one. But the polypropylene ones can exert more forces, which is why it was used more in the demos.
Okay, thank you.
Okay, thanks for the very nice presentation. I have, I don't know, maybe a too general question, but I wonder, you're using here two Delta robots to do like 2 fingers, and I wonder which is the advantage of using such a complex structure compared to like just 2 human-like fingers, more usual human-like fingers, maybe soft as well.
I see. So the goal of the project was so that we could develop it so that we could even have a bigger array of 64, so we could do in-hand manipulations. I think there are people working on the training of the human hands to like rotate the Rubik's cubes or do all that stuff. I think right now those hands are prohibitively costly right now, like minimum, I don't know, 15,000 to 25,000, depending on the. I think you could roll it with those hands as well, but learning those skills might be more difficult. Delta robots, their inverse kinematics have been solved for years, so they can try and map it. And so we also have people working on like the planning so that we can do in-hand rotations. But yeah, it's right now I think it's the cost and the difficulty in training.
Thanks a lot.
Thank you very much. I think Nancy has the microphone working now. Nancy, can we try to speak and please unmute?
Yes, can you hear me now?
Okay, wonderful. Yes, we hear you.
Sorry about that.
Okay, let me switch and have your presentation.
Okay, hopefully you can see my presentation now.
Yeah, that works. Please go ahead.
Okay, perfect. Okay, my name is Nancy Deaton, and I'll be presenting on our work towards a robotically steerable system for high dose rate brachytherapy. So high dose rate brachytherapy is a cancer treatment method in which hollow needles are inserted into the cancerous area, and these hollow needles are later afterloaded with radioactive seeds. This allows for the radiation dose to be applied within the affected area and thus directly to it, rather than external beam radiation, which has to come from the outside inward. This is improved upon. This is an improvement upon external beam radiation because it allows for much more customizable dose plans, such as the one shown to the right, as well as it allows for a higher dose of radiation to be applied to the affected area while avoiding normal tissue, which is very desirable. Steerable needles are desired for this application because they greatly improve which areas can be accessed, as well as they improve the ability to improve the ability to target where exactly the needles are desired, and the ability to avoid obstacles such as delicate structures or vasculature that the clinician does not want to injure. Prior work in steerable needles has been done looking at both passive steering and active steering. For passive steering, first is just base manipulation, which is adjusting the angle of the base of the needle in order to adjust the angle of the tip of the needle. This is currently how needles are just generally inserted as well when it is done manually, as well as bevel tip needles, which have an asymmetric tip such that they curve during insertion. And active steering methods include methods such as the pre-curved inner stylet and concentric tubes, which have inner tubes of different stiffnesses and curvatures that can thus be extended to affect the shape of the needle as it is inserted, and a programmable needle which alters the shape of the needle in order to adjust the angle of the tip and thus how it curves through the tissue as it is inserted, and finally tendon actuation, which involves a joint of some type at the tip of the needle. So in our work, we have proposed a tendon-driven steerable stylet for use in currently available commercial brachytherapy needles. So this tendon-driven stylet consists of a nitinol joint cut out of a nitinol tube and a support rod in the center, which prevents compression of the joint, given that the hollow needles are actually rather stiff comparatively. It can be inserted into a commercially available hollow needle for brachytherapy and is able to bend these hollow needles up to the desired 20 degrees in any direction. So we also created a theoretical model for this joint, and we first modeled what we called the stylet only, which is the joint and the supporting rod. And we modeled this by approximating the joint as a spring and approximating the rod as a cantilever beam, and assuming that the tendon force was equal, the moment created by the tendon was equal to the moment required to bend the rod plus the moment required to bend the joint. This allowed us to derive a relationship between the tendon pulling force and the bending angle. We then use this to get a combined Young's modulus and area moment of inertia of the stylet, which we were able to use to get a relationship between the bending angle and the tendon force for the stylet within the needle, which is given by the bottom expression here. So one key factor that we found that affected this force would be the moment arm, which was the distance between the tendon and the neutral bending axis. This for us was not always aligned with the central axis. We found that as the joint bent and compressed, it moved the rod to the outer edge of the bending joint, and thus the neutral axis shifted away from the tendon, increasing our moment arm and thus decreasing the force necessary to bend the system. So in order to analyze this, we identified some key parameters in the diamond cutting pattern of the joint, these being the member thickness, which is the thickness of the material left between the diamond cuts, as well as the acute angle radius of curvature and the obtuse angle radius of curvature of the diamond cuts. And we simulated joints with these different parameters using finite element analysis and ANSYS. And in these simulations, we also used a reduced number of notches, usually 8, though we also tested 10 in order to test our assumption that the simulation results could be scaled up to a full-length joint, which was approximately 3 centimeters long and much too large to put into an ANSYS simulation. So the results of these simulations show, as predictable, the joint with the largest radii of curvature and the thinnest members experience the lowest maximum stress. The joint sample in the middle with the same radii of curvature but thicker members as compared to the one above it experience a much higher maximum stress. And we also tested some designs with vertical members in a helix in order to increase joint stiffness. And this was also shown to have a high maximum value of stress. So we tested a lot of samples, but to summarize our key findings on this page, the finite element analysis simulations allowed us to compare maximum stress, maximum strain, tendon force, joint compression, and bending angle. In this, we found that the obtuse radius of curvature of the diamond cut didn't really have an effect on joint performance, but we also found that both the acute radius of curvature and the member thickness had a significant impact on the maximum stress and tendon force necessary to bend to the desired angle. We found that our assumption that the results of the finite element analysis simulation could be scaled up to a full-length joint held for the joint samples without the vertical members, but not for the joint samples with these vertical members. And we also found that the sample, again, with the lowest member thickness and the largest radii of curvature had the lowest maximum stress and strain. In order to validate these theoretical results, we performed some experiments by cutting 3 of the joint samples seen previously. We tested these joint samples both as the stylet only and as the stylet with the needle. In order to test these, we bent and unbent at a constant rate while collecting the tendon pulling force via a load cell and the bending angle via an electromagnetic tracker at the tip of the stylet or the needle. So the results of our experimental tests show that our experimental results fit our theoretical model very well, both for the case of the stylet only and for the case of the stylet within the needle. And this was tested for 2 samples without the vertical members, and both of them held very well. We also saw that the hollow needle contributes significantly to the stiffness of the overall system as compared to the stylet alone. And this is partially due to the fact that the stylet is within the hollow needle, so the moment arm of the tendon is so small, and thus the area moment of inertia of the hollow needle is relatively large. Therefore, it takes a much larger tendon force to bend the stylet within the hollow needle as compared to without the hollow needle. Finally, we saw that the trend continued as seen in the ANSYS simulation. So again, here we see that experimentally, The joint sample with the thinnest members and largest radii of curvature also required the lowest tendon force in order to bend to the target angle. In conclusion, we have proposed a tendon-driven steerable stylet, which is capable of universal bending within a commercially available hollow brachytherapy needle and has been validated to bend this needle up to the target 20-degree angle. Furthermore, we have shown that the parameters can be tuned via ANSYS simulation and that our theoretical model holds. In the future, we will work to characterize the external forces that could affect the system design and performance, and we will also evaluate the steering of the needle in vivo. So I would like to acknowledge Emory University and the National Science Foundation for funding, and can take any questions now.
Questions for Nancy? Yeah, please go ahead.
Hello. Oh, thanks for the interesting analysis and all. So I wonder, these are steerable needles that are being inserted into tissue and possibly rotated at the base. Do you think that modeling those forces of the tissue interaction along with the rotation of the base is important in optimizing the design?
I think that it is important in short, yes, I think it is important in optimizing the design because here we were bending in free air without resistance, but if we were, for example, if we were to try to meet that target design at that target bending angle with a lower tendon force, while with the resistance of tissue, then we might need a less stiff joint. So I definitely think that is important to consider in design.
Other questions? Yeah. Well, please, the in-person speakers, you can come to the front, and you also, the other speakers who are online, please stay with your cameras, and we are going to now have the discussion session. So, okay. All right, we still missing one more. You have the list? Huh? No, I mean on the screen. Okay. Harsimran Singh. Yeah. All right, we have everyone. So perfect. Yeah, this is amazing. We have people from all around the world sitting on the screen, and we have you. So now we're going to spend a few minutes discussing this session, and after that, I would like to just let everyone know that we are going to take a photo of those participating here in person with everyone who is participating online. And for that photo, we will ask everyone to turn on your cameras right after the session. So just get ready, and what we will do is we will move to the front and we will take a photo from there. It will be in a physical photo that we will take from that side. All right, so let's start the discussion, and we are going to have questions from those who are participating online or from those who are sitting here in person. Yeah, please go ahead.
You touched on this a little bit, but I'm interested in other people's perspectives as well. For these human-robot studies, how important is really using a human for the final validation, and how early should a human be brought into these studies? I mean, some of these that are medical studies, you need to have good assurance, or the compliance studies, you need to have good assurance you're not going to hurt someone. For something like Tom's work, where there's not really a risk of hurting anyone, but there's children involved. So when is the right time to start involving humans into these studies and experiments?
Very good questions. Who would like to start?
I can start this a little bit. I mean, it's super context specific. Like, I have no idea. Medical robotics and all of that is way different, obviously, like Chris said. I think where I work with kids, logistically it's super difficult because you need approval from an IRB and stuff like that, which is good to make sure we have. But earlier than we do, especially for low cost, I think we do a ton of convenience sampling of college students and of Mechanical Turk, and then we say our systems are going to work in our field a lot of the time. And to me, it's kind of funny because it's like making a website that you never give to anyone. You say, my website was designed perfectly. But I'm super opinionated, and I work very different than what everyone else kind of does.
Do you have further comments?
Hello? Well, I don't really work with human studies right now, but I am trying to develop a human interface right now to teach robots easier. I think it is important to get a lot of feedback early on in the design before you go too far and then figure out it's not as user intuitive as you thought. Like, I think a lot of elderly people prefer human, speech to give instructions to robots as compared to, programmers, we just like to give command codes, command line. So it's just, I think.
Nancy, would you have any comment about human subject?
Yes, for our field of surgical robotics, we will involve a clinician as early as we think it is in a presentable state that the clinician can actually work with it and we can get something out of that. But we will be testing in hydrogels a lot of the time, or in animal models, usually ex vivo, but we will not be doing clinician. We will not, at least for our field, we do not actually test in patients, not in labs. That would be a company picks up our work and is through the FDA. So.
Indeed. Harsimran, in haptics, this is very important, the human interaction, and it's all about rendering that environment. So, any comment?
Yeah, sure. So, because you have force feedback involved, you have to firstly make sure that your system is stable. If you're using small devices like a desktop device, like a Phantom Premium, Omni, or Falcon, it's okay because the maximum forces could be about 20 newtons or so, which are safe. But if you're using a robotic manipulator arm, to use that as a force feedback device, then firstly, you have to be sure that the device is very stable to work with and your controllers actually work. Secondly, we do perform some very basic pilot studies to know that the user studies that we have designed or planned out is going according to what we want, and the results are somewhat in line with what we are looking at. If not, then we either redesign the user studies or modify the controllers to see what sort of data we get. Yeah, but in the end, I guess if we have to do some space teleoperation tasks, we only have 1 or 2 astronauts, so we don't have that many candidates. So we have to be very accurate with what we are doing and or design the user studies very accurately.
Okay. Well, I guess, Thomas, also you have a very important role for the human not to be injured, and in a way, the interaction with the human is going to be really interesting, especially with your approach of a different area in the body that has different characteristics. Could you please comment?
So you meant myself, right?
Yeah, you're here.
Okay. I understood Thomas, sorry. So, yeah, so I would say in the case if you do those collision experiments with humans,
I'm sorry, I said Thomas, I meant Sebastian.
No problem. So yeah, if you do collision experiments with humans, this should be the very last step, because it's very time consuming. You need a lot of volunteers, and last but not least, you need the improvement by an ethical committee. So all in all, cost intensive, time consuming, and lots of volunteers. So I think, yeah, you should do it at the very end, and just at a point where you're very sure that during those experiments nothing can go wrong, or that you even use not a real robot for such experiments. For example, at our institute, we use a pendulum with different where you can go outside from the center point by different angles and attach different weights, so you exactly know what is the kinetic energy which will hit the human.
Okay, thank you, Sebastian, and thank you for presenting 2 papers. That was remarkable in one session remotely. So I agree with you, and do not try the method of Sami Haddadin, where the researcher becomes the subject and undertake really dangerous maneuver for the sake of safety. Well, thank you very much all for this interesting discussion, and following a very interesting session in the presentation.